Welcome to today's lecture. Today we're going to be talking about correlation and correlation coefficients. So, overview of today, we're going to talk about what correlation coefficients are, computing them, interpreting them, and then also a very similar and related concept called the coefficient of determination. So correlations are a way of expressing relationships between two variables. Basically, we take our data in a scatter plot and we fit a line over that, and we compute a numeric estimate of how correlated those numbers are. That numeric estimate is called R. It reflects the correlation between variables x and y as shown here. Correlations have to do with the relationship between two variables, exactly two variables. So different types of correlations between variables x and y, depending on whether we're looking at continuous or nominal or ordinal or different types of variables. So this table is from the book, and I think it actually helps clarify things a lot. With two things that are nominal, we can calculate the correlation between, say, voting preference and gender. We can also calculate the correlation between things here at the bottom, so number of problems solved and age. Depending on which type of data we're using, we're going to have different types of correlations. We are going to be spending most of our time talking about the Pearson correlation coefficient. So Pearson R is used for continuous data. We assume that data is normally distributed, sort of like we have for many of our topics here. We assume linearity and homoscedasticity, or equality of variance. If we're using a Spearman rank correlation, which again is here the second to the bottom, ordinal versus ordinal, that's where we use a Spearman ordinal rank correlation. We don't assume that normality. Well, correlation coefficient is going to give us a number between -1 and 1. The closer to 1, or the further away from 0, that means the stronger the relationship. The closer to 0, the weaker the relationship. The sign, again, tells us about the direction, so a positive or greater than 0 is a positive relationship. Less than 0 is a negative relationship. That's not a values judgment, that's a literal numeric judgment. So it doesn't mean it's a good thing if it's positive and a bad thing if it's negative. It just literally means we call it a positive correlation. That positive correlation we can also call a direct correlation, not a direction, so that's a typo, when variables are changing in the same direction. So an increase in one is associated with an increase in the other. Negative correlation is what's called an indirect correlation, when they change in opposite direction. So if x increases, y will decrease. So here we see as x increases, we see examples of what might happen to y. So the more time you spend studying, the higher your test score will be. Hopefully that's the case here. That would be a direct or a positive correlation between those two. We can also talk about the more we exercise, the less we'll weigh. That's a negative correlation, and I think that's a good example of why it's not a values judgment here. It just means it's an indirect correlation. If one variable increases, the other goes the other direction. Finally, the less time you take to complete a test, the more questions you'll get wrong. That's a negative correlation. So we can plot these out. As we saw earlier in the semester, we can get a scatter plot. Scatter plots are visual representations of the relationship between x and y, or two variables. We can see here this is an example of a positive correlation, and actually it's an example of a perfectly positive correlation. As x goes up 1 unit, y goes up exactly 1 unit. So that means it's perfectly positive. It's not even an approximate relationship, it's perfectly linear. Here we have a strong positive relationship, but we can see it's not perfect. As x goes up, y goes up sometimes a little bit, sometimes a little bit more. Here we generally see, though, that the more time you spend exercising, the more calories that you might burn. Some of the variation in that might be if you're just having sort of a leisurely walk and you spend an hour walking, you might not burn as many calories as somebody who went to an intense say spin class for only 45 minutes. So that's an example where there's a relationship, there's a correlation, but it's not a positive, it's not perfect. Here we have an indirect relationship. As alcohol consumption increases, judgment will decrease. And again, we may get some variation in there in terms of just how much alcohol and judgment has been impacted, but in general, the more that one would consume alcohol, the worse their judgment would get. So that's going to be a negative relationship. We can see it's very strong. That's the pattern that we see on the X and Y relationship there. So what do we do in order to create a scatter plot? One of the great things in Excel is that we can do this with basically 3 clicks. So first we highlight whatever data we want to use, and that will just, we'll do that how we've always done it. Go up to the Insert menu, click Insert Scatter or Bubble Chart icon. There's a little icon that looks just like a scatter plot, and voila, that's what we get. The first thing that it'll spit out may not be properly formatted, so you might want to improve the labels, the formatting, all that kind of stuff. Make it reflect your best work. We can also calculate the correlation coefficient. Here we'll need to go into an empty cell and start typing the formula equals CORREL. Then start typing where our arrays are, or our 2 sets of data. Here we're looking at cells A2 through A11 as array 1, and array 2 is B2 through B11. Then we click enter, and Excel will give us that the correlation here is 0.69. Great, so we've learned how to calculate correlation coefficients. We've learned how to visualize the relationship between those 2 variables. So what do we do once we have them? We can calculate what's called a correlation matrix. Here we can put all of the correlation coefficients that we've calculated for several different variables into one single table. So here again, what we're looking at is not the relationship between all 4 of these variables, but the relationship between exactly 2 of these variables. So in the table we can see that the correlation between income and education is 0.35. So that's not a perfect relationship, but we can see that as education increases, income also tends to increase. We can also see that there's a negative correlation between attitude and education. So attitude here is a measure of the attitude on some assessment that has been performed. And the more education that someone has, the less that they scored, the lower they scored on this attitude measure. So we don't know whether the attitude measure measures a good attitude or a bad attitude or only certain parts of an attitude. All we know is that as education increases, attitude tends to decrease. Or as attitude increases, education tends to decrease. Same thing with attitude versus income. We can also then look at other correlations, and keeping in mind the concept that we talked about several slides ago, that the strongest correlation is the higher the number, the further away it is from 0, the stronger that correlation is. So in this case, the strongest correlation is between voting and attitude. The lowest correlation, or the weakest correlation, is between income and attitude. So even though income and attitude has a correlation of negative 0.19, it's actually a weaker correlation than the correlation between attitude and education, which has a lower number, negative 0.21, but is actually further away from 0. So it has a stronger negative relationship than the relationship between attitude and income. Sometimes you can get very, very, very strong negative correlations, negative 0.7, negative 0.8, negative 0.9, and that can sometimes trick you into thinking that that's a very weak relationship, when actually it's a very strong relationship. So let's talk about how we categorize correlation coefficients. So anything that's above about 0.8 we'd consider to be very strong. 0.6 to 0.8, strong. 0.4 to 0.6, moderate. Once you get below about a 0.2, we consider that a weak or really no relationship at all. If you're at a 0.01, there's really nothing going on there. It's just that it doesn't happen to exactly equal 0. So let's take a pause here and try to interpret some of these correlation coefficients. So the correlation coefficient between the time spent running and BMI is negative 0.8. So would this mean that there is a negative or a positive relationship between these two activities? There's a negative relationship. So the more time you spend running, the less your BMI. Or the less your BMI, the more time you spend running. You can see here that we're not interpreting this as causing one thing or the other. All we're saying is that the relationship, as one increases, one goes a different way, or one goes the same way. So the correlation coefficient for smoking and lung cancer is 0.9. Here we see this as a positive relationship, and thinking back to our last slide, what strength of relationship would this be? This would be a very positive, a very strong relationship. It's above 0.8, so it's the strongest category we have. Correlation between number of siblings and GPA is negative 0.1. We can see that there's a very weak or no relationship between these two variables, but to the extent there is a relationship, it's negative. So the more siblings you have, the lower your GPA, or the lower your GPA, the more siblings you have. Hours sleeping and GPA is positively correlated, and that's a modest correlation. So one thing to distinguish here, as I think we probably saw in the last slide, is that there's a difference between correlation, which is the relationship between two variables, and causation, which is that one causes the another. It's important to point out that just because two variables are very strongly correlated, that doesn't mean that they've caused each other. We've talked a couple times in this course about the relationship between ice cream sales and drowning. It does not mean that ice cream sales cause drowning. So we can use a correlation coefficient to do something else too. We talked about variance when we were talking about range and standard deviation, but we're talking here about variability. And we want to explain the variability in one of our variables as it's described, as it's explained by another variable. So here we can see, this is an example of a chart that shows some of the shared variance between three different concepts. So variance is explained by what's called the coefficient of determination, the percentage of variation in y that's explained by x. We calculate that as the square of the we calculate that, there's a typo here, calculate that as the square of the coefficient of correlation, the correlation coefficient, or r squared. So to reiterate, r is the coefficient, is the correlation coefficient, r squared is the coefficient of determination. So for example, if the correlation coefficient equals 0.7, 0.7 squared equals 0.49, or 49%. So 49% of the variation in y can be explained by x. And again, that doesn't mean it's causing it. All we know is that if we know something about x, we have a little bit more information on y. So the higher the better. It will always be between 0 and 100%, or 0 and 1 if we're using decimals. Will it ever be negative? The answer to that is no. Since we're squaring it, it will never be negative. Even if we had a negative 0.99 and we squared it, we still end up with a positive number. So again, when we square things, it ends up that what we get is the coefficient of determination. It's that middle area in that Venn diagram there. The coefficient of alienation is the opposite of the coefficient of determination. It's the percentage of variation that is not explained by the other variable. So it's essentially a measure of the non-association. The formula for calculating it is 1 minus r squared. So taking our previous example, if the correlation coefficient was 0.7, our coefficient of determination was 0.49, our coefficient of alienation is 0.51. Again, it will be between 0 and 100%, and it will never be negative. So here we can see the two crescent moon shapes are our coefficient of alienation. So here we can visualize our coefficient of determination versus our correlation coefficient. We can imagine two circles that are completely non-overlapping if we have a correlation coefficient of 0, or coefficient of determination of 0. If we have a correlation of 0.5, we can see that 25% of the variation in y is explained by variation in x. and when we get towards the bottom, 81% is. So here we have the coefficient of determination depending on zombies and flesh-eating cannibals. We can see that in the center there, somebody who is both a zombie and dead or resistant to, someone who's both a cannibal and resistant to pain would be a zombie. And that's that shared area there. The coefficient of determination is the red shaded area, and the coefficient of alienation is the pink shaded area. One thing to really hit on here hard is that correlation does not equal causation. We've calculated several ways of expressing the relationship between two variables, but that does not mean that things are causing one another. So showing how two variables are related to one another is a way of giving a useful overview of this description of how things vary, and that we can quantify it in order to be able to have a shared language about just how strong that relationship is, whether it's positive or negative, and so on and so forth. So with that, that will wrap up our content for correlation coefficients. Please do take a minute or two to do a couple things with some of the data that we have thus far. There isn't a specific new data set for this lecture, but what I would like you to do is just take a little bit of time to go back through some of our old data sets and practice calculating correlation coefficients between the two. Once you have a correlation coefficient, or R, calculate that coefficient of determination and coefficient of alienation. You can then start to see a little bit more about what sort of numbers you tend to see. Plot it out and see what a correlation coefficient of 0.9 is. See what a correlation coefficient of 0.2 is. It'll help just sort of orient you to what these things look like in real life. So with that, thank you very much for listening. Look forward to talking next time.